Welcome back. Today, we are looking at something truly fascinating, especially if you're preparing for those crucial Cambridge exams. We often think of mathematics as just this rigid set of arbitrary rules or numbers stuck on a chalkboard. But in reality, it's an incredibly powerful toolkit. It's literally a lens through which we can predict real-world events, bring order to total chaos, and mathematically manipulate visual space. Today, we're going to take a journey starting from a real-life physics accident all the way to the abstract manipulation of complex curves and functions. Let's get started. Okay, let's dive right into today's assessment breakdown. We'll be moving through 4 key areas: the runaway car model, discovering rectangular hyperbolas, decoding linear functions, and finally, shifting and transforming graphs. Starting with Section 1, the runaway car model, where we apply algebra directly to real-world physics. Imagine this. A driver parks his car on a hill with a constant gradient, completely forgets to pull the handbrake, and the car starts rolling down. Luckily, or well, maybe unluckily for the driver's insurance, the entire incident is captured on CCTV. Looking at the raw data here, it tells a really compelling story of acceleration. In the very first 2 seconds, the car rolls just 0.2 meters, but in the next 2 seconds, it rolls another 0.6 meters to hit 0.8. By the 12th second, it has covered 7.2 meters. The distance is increasing at a nonlinear rate. It's actively speeding up. If we were to plot this, time against distance, we wouldn't just get a boring straight line, we'd get a curve sweeping upwards. And this brings us to the immediate stakes of our mathematical modeling. Looking at the data, we only know what happened up to that 12-second mark. But what if the road is exactly 120 meters long? How long is it going to take that runaway car to reach the very bottom? We can't just guess here. We need to shift our focus from historical CCTV data to actual future prediction. To crack this runaway car problem, we follow a precise mathematical modeling process. Step 1 is to plot the time versus distance data to visualize the curve. Once we clearly see the shape of that curve, which is likely a quadratic given the acceleration, step 2 is to find the algebraic equation that perfectly fits it. It's kind of like finding the secret code that governs the car's exact motion. Once we have that equation, step 3 is simply substituting 120 meters for our distance variable to calculate the exact time it'll take to hit the bottom. Boom! We've turned a physical, chaotic event into a perfectly solvable equation. But before we declare the case totally closed, we have to ask ourselves, what real-world factors might affect the validity of our 120-meter estimate? Math models a perfect world, but reality is messy. What if the hill's gradient isn't perfectly constant the whole way down? What about friction from the tires, or wind resistance as the car speeds up? What if the steering wheel locks and the car hits a curb? Our equation gives us a mathematically perfect estimate, but real-world variables always introduce a margin of error. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Moving on to Section 2, Discovering Rectangular Hyperbolas, where we explore some entirely new geometric shapes. Now that we've seen how math grounds us in reality, let's pivot into a bit of theoretical exploration. Say hello to the rectangular hyperbola. It is defined by the equation x squared minus y squared equals a squared, where a is a constant. It's an absolutely fascinating concept. If you imagine a 3D cone and literally slice it vertically, the curved edges you reveal form a hyperbola. But looking at this equation right now, it's not very friendly for graphing, is it? We need to manipulate it. To really understand this shape and easily graph it on your display calculator during an exam, we need to make y the subject. Let's walk through the logic of this algebraic manipulation. We start with our base equation. Next, we subtract x squared from both sides, leaving negative y squared equals a squared minus x squared. To clear that annoying negative sign, we multiply everything by -1, flipping it to y squared equals x squared minus a squared. Finally, we take the square root of both sides. And remember, taking a square root gives both a positive and negative result. So y equals plus or minus the square root of x squared minus a squared. And there we have it. We can now actually input this into a graphing calculator. If we set our constant a to 1, we get this beautiful base shape. 2 mirroring curves moving infinitely outward but never quite touching those intersecting invisible boundary lines, which we call asymptotes. But here's where it gets incredibly powerful. By changing the value of that constant a, we dynamically determine its effect on the entire shape of the graph. We can widen the curves or bring them closer together. We are literally manipulating visual space just by changing one single number. Stop scrolling, subscribe to our YouTube channel Ace the Exams at acexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, on to Section 3, Decoding Linear Functions. This is the underlying matrix of graphing. We've looked at complex curves, but now let's break down the rules of manipulation using the most fundamental shape out there, the straight line. Linear functions take the standard form f of x equals ax plus b. Let's look at the role of a. This is the gradient. It completely dictates the steepness of the line, whether it's a gentle, easy slope or a steep mountain climb, and whether it goes up or down. Now consider the role of b. This is the y-intercept. It controls the vertical position of the line, literally exactly where the line crosses the y-axis. Just 2 simple variables giving you complete, total control over the line. And this brilliantly illustrates how we apply those rules in practice. Look at these 4 functions. For y equals x plus 3, the gradient is an invisible 1 and the intercept is 3. It crosses the vertical axis right at positive 3. For y equals x minus 2, it has the exact same steepness, a gradient of 1, but it crosses further down at negative 2. Then we have y equals negative 1/2 x minus 4. That negative gradient means the line is pointing downwards, and it crosses way down at negative 4. Finally, y equals 2x plus 1 is our steepest line, pointing up like a mountain climb, crossing at positive 1. Just by looking at a and b, you can instantly visualize the line in your mind without ever even drawing it. Which brings us to our final section, number 4, shifting and transforming graphs. It's time to master mathematical manipulation. We are moving into our final phase, acting as true mathematical code breakers. Instead of just changing the steepness of a line, we are going to learn the precise rules to physically shift entire complex functions across the axes without changing their shape at all. Let's look at 2 rules that seem incredibly similar but behave entirely differently. First, y equals f of x minus 3. Because the minus 3 is outside the function, it affects the total y value. This creates a vertical shift straight down the y-axis by 3 units. Conversely, for y equals f of parenthesis x minus 3 parenthesis, the minus 3 is inside the function, attached directly to the x. This creates a horizontal shift, and here is the real trick. It shifts to the right by 3 units. I know, it feels slightly counterintuitive, but subtracting inside the parenthesis actually moves the graph in the positive x direction. Let's see exactly how this maps out with some real coordinates. We have 3 original points, A, B, and C. Let's look at point A, sitting at -2, +1. Under our first transformation, shifting vertically down by 3, the x stays exactly the same, but the y drops from 1 to -2. Now look at point A under our second transformation, shifting horizontally right by 3. The y stays at 1, but the x shifts from -2, moving right 3 spaces to land precisely at +1. The entire shape moves smoothly, anchor point by anchor point, perfectly preserving its geometry. Let's see how this builds when we apply these exact same rules to a standard quadratic curve, that classic U-shape of y equals x squared. If we want to take that curve and slide it perfectly to the right by 4 units, we attach the shift directly to the x, giving us y equals parentheses x minus 4 parentheses squared. If we want to drop the whole curve down by 4 units, we apply the shift to the total function, giving us y equals x squared minus 4. Once you know these rules, you can place any shape anywhere on the grid, perfectly on command. And that brings us to the end of our strategy session today. We started with raw CCTV data of a rolling car, mapped its physical acceleration, explored the infinite bounds of rectangular hyperbolas, and learned to decode and manipulate visual space with strict transformational rules. The tools are all right here. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.